Okay, so useful remark. So say that you can compute both these guys. Well, then actually their product will just be 1. So, they're the inverse of each other. So it doesn't matter which one you compute. You can compute whichever one is the easiest to compute, no matter which one of the two you need. And one way to see that is that, in fact, we're looking at the determinants of these matrices that tell us the relation between the variables. So if one of them tells you how delta U, delta V relate to delta X, delta Y, the other one does the opposite thing, it means they're the inverse matrices. And the determinant of the inverse matrix is the inverse of the determinant. So they're really interchangeable. I mean, you can just, compute whichever one is easiest. So here, if you wanted, dr d theta in terms of dx dy, it's easier to do this and then move the r over there than to first solve for r and theta as functions of x and y and then do the entire thing again. But you can do it if you want. I mean, it works. Oh yeah, the other useful remark. So I mentioned it, but let me emphasize again. So now the ratio between du dv and dx dy, it's not a constant anymore. Over there it used to be 5, but now it's become r or anything. I mean, in general it will be a function that depends on the variables. So it's not true that you can just say, oh, I'll put a constant times du dv. Yes?
With uv you change from Cartesian coordinates to Cartesian coordinates. So when you change the polar coordinates, will the approximation?
It would still work the same. You could imagine drawing a picture where r and theta are the Cartesian coordinates and your picture would be completely messed up. It would be a very strange thing to do, to try to draw, I mean, I'm going to do it, but don't take notes on that. You could try to draw a picture like that, and then, a circle would start looking like, a disk would look like that. And it would be very counterintuitive, but you could do it, and that would be equivalent to what we did with the previous change of variables. So, in this case, certainly you would never draw a picture like that. But you could do it. Okay. Okay, so now let's do a complete example to see how things fit together, how we do everything. So let's say that we want to compute. So I have to warn you, it's going to be a very silly example. It's an example where it's much easier to compute things without the change of variables. But it's good practice in the sense that we're going to make it so complicated that if we can do this one, then we can do them all. So let's say that we want to compute this, and of course it's very easy to compute it directly. But let's say that for some evil reason, we want to do that by changing variables to u equals x and v equals xy. Okay, that's a very strange idea, but let's do it anyway. I mean, normally, you would only do this kind of substitution if either it simplifies a lot the function you're integrating, or it simplifies a lot the region on which you're integrating. And here, neither happens. So, but anyway, so the first thing we have to do here is figure out what we are going to be integrating. Okay, so to do that, first we should figure out what dx dy will become in terms of u and v. So that's what we've just seen, using the Jacobian. Okay, so the first thing to do is find the area element. And for that we use the Jacobian. So, well, let's see. The one that we can do easily is partials of u and v with respect to x and y. I mean, the other one is not very hard because here you can solve easily, but the one that's given to you is partial of u and v with respect to x and y. So partial u, partial x is 1. Partial u, partial y is 0. Partial v, partial x is y. and partial v partial y is x. Okay, so it's just x. So that means that du dv is x dx dy. Well, it would be absolute value of x, but x is positive in our region, so at least we don't have to worry about that. Okay. So now that we have that, we can try to look at the integrand in terms of u and v. Okay, so we were integrating x squared y dx dy. So let's switch it. Well, let's first switch the dx dy. That becomes 1 over x du dv. So that's actually xy du dv. And what is xy in terms of u and v? Well, here at least we have a little bit of luck. You know, xy is just v. So that's v du dv. So in fact, what we'll be computing is a double integral over some mysterious region of v du dv. Okay. Now, last but not least, we'll have to find what are the bounds for u and v in the new integral, so that we know how to evaluate this. In fact, well, we could do it du dv or dv du. We don't know yet. Oh, amazing. It went all the way down this time. Okay. So it could be dv du, if that's easier. So let's try to find the bounds.